Hello and welcome to the Open Systems Media webcast titled How SOSA Aligns with Current Open Standards. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. Our speakers today are Rodger Hosking, Vice President and Co-Founder of Pentek, Tran, Vice President Global Marketing at Aitech Systems, and Dinesh Jain, Product Manager with Military Electronics at Smart Embedded Computing. Today's webcast is sponsored by Aitech Systems, Pentek, and Smart Embedded Computing. Now, before we get started, I have some housekeeping announcements. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. Today's webcast will consume about 45 minutes, leaving the remaining time for the question and answer session. Now, let's take a look at that viewing console. It has some important new features I want to run you through. It consists of a set of windows that you can close, open, move, resize, and maximize to your personal preference. On entry, you'll see a picture of our presenter in the presenter window, biography in the speaker bio window, the presentation slides in the slides window, and the Q&A window that enables you to ask questions during the event. There are a set of 7 icons across the bottom of your screen. Clicking the icon on the far left will reset your viewing area to the default configuration. The rest of the icons will open or close their corresponding window. You can hover your mouse over each icon to show which window it controls. The handout icon third from the right opens the handout window, which has the presenter slides in PDF format to follow along with or download for future reference. The Q&A window enables you to participate in today's event. Simply type a question into the Ask a Question text box and hit Submit. If you have a question intended for a specific speaker, please note so at the beginning of your question. Otherwise, I'll hand out the questions equally to all of our speakers. If you have a question pertaining to the webcast operation itself, one of our technicians will get back to you during the webcast. I encourage you to ask questions throughout the event while the question is still fresh in your mind. We'll address as many questions as we can during the closing Q&A session. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the webcast with more information. This webcast will be archived online at the URL shown on your screen and be available within 24 to 48 hours. Once up, it'll be available for 1 year. So let's get started. I'm going to turn it over to our first speaker, Rodger Hosking. Rodger, take it away.
All right, John, thank you very much. And thanks, everybody, for attending today. So I'm going to be talking a little bit about and VITA. The trade organization and the standards organization are aligned and how they work together and how they play back and forth. So what I'm going to do is cover several different topics. Just going to do a little background on a few first slides of how SOSA got started and then what its main objectives are. Talk a little bit about the technical standard, how SOSA adopts open standards, and then the strategic relationship between SOSA and VITA, how classified information is handled, and then which VITA standards have been adopted so far in SOSA, along with some examples of those, and then finally some useful links if you need more information. So I'll first get started with a little bit about what the Open Systems Initiative, often called the OSA or Module Open Systems Architecture, which came down from the US DoD. What it's intended to do is all of these things and enhance the competition, to stimulate technology refresh so we can get new capabilities more efficiently and quickly, to promote innovation in the community of vendors and contributors to the effort, save cost, avoid costs, and then also to improve interoperability between products of different vendors. And that is these are the main objectives coming down from the US DoD. We basically saying we need these things to make our defense services more efficient and effective. So after hearing those directives coming down from DoD, each of the 3 services decided to work on their own implementation of how those objectives should be met within their organization. So the Navy organization took on a program called HOST, which we might hear a little bit more about today. And then the Army took on the CMOS, defined that, and the Air Force took the Open Mission Systems. These are all different implementations of these open principles that we talked about before. But as they as they evolved, each of those different organizations pulled in different standards that were useful to those organizations. And if you'll notice that all three of them found that OpenBPX was extremely useful. You'll see some other common features like RedHawk, which we'll be hearing a little bit more about today as well. But after they kind of came up with these standards, they realized, and the government also realized, that there was some duplication of effort. And so the three services decided to join forces into what's called the SOSA Consortium for the Sensor Open Systems Architecture. And this is run by the Open Systems, the Open Group. Oops, let me just go here. And this then is the organization that defines and maintains the SOSA initiative. So this is kind of how SOSA came about, and you can see kind of its DNA here on this slide. Just talking a little bit about what the technical architecture is within SOSA. It's very modular, and it defines how things behave at the interface level and how to interface with other modules. That's a very well-defined part of it. There are three main criteria. It has to be open in terms of it's widely available, like OpenBPX, based on open standards. It's consensus-based, and it has a compliance or conformance validation process. This is a little different than what most of the standards, like other VITA standards, have. So that is a new thing. And it also uses what's called the gray box concept. And what that says, quite simply, is it defines what the box does. It defines how the box interfaces to other boxes and other parts of the systems. But it doesn't define exactly how the box performs its functions within the box. And it doesn't define the intellectual property that's inside the box. So what that does is it helps the people who are developing and inventing new ways to do things. It kind of protects their intellectual property, but yet still provides the advantage of that function in a very easy to connect offering. And that's really a big part of what the SOSA is all about, and that's part of the interoperability, of course. So in terms of defining this architecture, how is it implemented? SOSA publishes a technical standard, and the technical standard is the defining document that pulls in a lot of different standards and defines exactly how they will be used and which ones will be used. It is released periodically. So far, it's only been released as preliminary snapshots of the standard as it evolves over the last couple of years. Currently, Snapshot 3 is the latest standard. We expect the full release 1.0 to happen in mid-21, this summer, basically. And after that, U.S. and foreign defense organizations can submit their products for SOSA certification. Again, that's that conformance certification process I talked about. But the published document is open for all to use. And we even have some organizations outside of the U.S. who have been invited to participate in the SOSA consortium. So this is definitely partly and will eventually become, we believe, a very important world standard for all defense electronics. We're already seeing it's having some influence outside the U.S. So now let's talk about how the SOSA technical standard incorporates VITA standards. So some of the standards within SOSA, it can, you say, kind of leverage from them, okay? And for example, it could say, I want to adopt a particular plug-in card, and I want to set an order of precedence in order to apply those standards. So it pulls apart some definitions within VITA, and it shows how and which parts of those definitions will be used. Some of the recommendations in VITA have become rules. In other words, they were optional in the VITA spec, but SOSA said this is really a good recommendation and we want to make it a rule. And some parts of the SOSA spec are more restrictive extensions of the VITA standards. And one of those would be there's only a limited number of slot profiles that VITA 65, which is Open VPX, defines that is being adopted by VITA, by SOSA, sorry. And then on the other hand, some of the VITA standards have been adopted by other standards such as HOST. You can see here in the diagram, this is VITA 46.11, which is platform management. And SOSA liked the way that the HOST standard adopted VITA 46.11, and so it said, okay, we're going to just take it exactly the way that the HOST standard adopted it. And some recommendations from SOSA that needs have been identified lead to new standards in VITA. So let's see a little bit about how that happens. Let's see, now I think I skipped ahead too far here. Here we go. So one of the ways that happens is that you take the membership of VITA, which is worldwide, and anybody can participate, but the open group, which is the group that manages SOSA, is only open to U.S. citizens. So you can have discussions within SOSA that are sensitive or classified that could not be held in the VITA Standards Organization. So what happens is SOSA can pass along some sanitized recommendations to have a new feature added, a new function added to the VITA specification without really specifying why that function might be needed. And then once VITA analyzes the requirement, they can vote and decide that it should become part of a VITA standard, and then SOSA can adopt that part of the standard that was added to become part of the SOSA Technical Standard. So that's kind of the way some of the new features that have come up in VITA standards in the last few years have been influenced by discussions within SOSA. So let's take a look at some of the standards that VITA spells out that have been adopted so far in Snapshot 3. These are likely to remain in the Technical Standard 1.0 when it's released. The first group of those standards is plugin card specs for XMC modules, VPX, Open VPX. Those standards have been adopted by SOSA, and again in special ways, but they're an extremely important part of the SOSA standard. Also, protocols and mapping. In other words, how is PCI Express mapped? Serial Rapid I/O, signal mapping for I/O signals between a PMC or XMC and the rear panel. And then the last one is quite important too. This is the VITA Radio Transport Protocol, which defines how signals, digital signals, are sent, with typically radio signals, digitized, how they're sent around in the system. It standardizes the way they're being, those signals are being packaged up and identified so that they can be used by multiple applications very easily. System management. This manages and monitors the health of the system. That's VITA 46.11 has been adopted. We also have a lot of mechanical, power, and thermal management standards within VITA. Now you see them all listed here for all different kinds of cooling and mechanical structures, power supplies. These have all been strongly inherited by SOSA. And then some new things that have come out in the last 2-3 years or so have been some of the optical and RF backplane interconnections that have, a lot of which have been inspired and extended by feedback from the SOSA group. Just take a look at some of those last standards. For example, this is a backplane, and what it does is it shows apertures that have been opened up in the backplane for VPX chassis, and these openings are called apertures. They're used to handle inserts that can be attached by screwing them into the backplane that have different functions. In this case, you have an optical 24-lane ferrule that goes into this aluminum housing that screws into the backplane, but you could put something else in there as well without having to get a new motherboard, a new backplane rather. Similarly, here's an RF housing that can go in to the P2 opening, P2 aperture. And again, the idea here is by doing that, what you can do is have a single backplane serve a lot of different applications simply by installing the appropriate aperture to handle the type of I/O that you need. Take a look at some other examples of complete boards using the nano RF and the SMPM coaxial RF connections. You can, for example, put RF I/O on a 6U card. Again, this is another SOSA definition for a 6U board. You can also have optical and RF mixed, and this is quite popular. Here what you can see is a mixed optical and RF connection, and you actually see two different housings, each with 10 RF coaxial connections and 2 MT, each one has a single, so there's a total of 2 MT ferrules for the optical I/O. And these are quite popular for getting a lot of the I/O signals out to the backplane instead of having it come out through the front panel. That really does help with maintenance and reliability. So how are these applied? What good do they do? And they really do a lot. A very new technology is RF SOC, which is radio frequency system on chip. This is a chip from Xilinx that we put on a board level product. And you can see a block diagram here. It's got a lot of A to D converters, D to A converters, dual 100 gigabit Ethernet interfaces, ARM processor. So all of these things need to be connected. And fortunately, a lot of these new standards that have come out support it very well. So the 20 RF I/O is handled very nicely by that connector that I showed you on the previous page and using VITA 67. You have also, in the optical I/O, you can have 2 lanes of 4 25 gigabaud lines that will give you 200 gigabit Ethernet optical ports out the rear panel. Radio clocks are defined in VITA 65 for synchronously clocking multiple cards for synchronous phased array applications. You've also got some copper planes like 10 and 40 gigabit Ethernet, and a single LVDS expansion plane or PCI Express that can be put also on copper. These are defined in VITA 65 slot profiles. And last, you have a lot of I/O that's suitable for a CPU that is defined in VITA 65 as well. So taking advantage then of power and cooling is also, of course, very necessary and supported. It's hard to show here, but of course that's part of the game as well. So just to wind up here, I want to show you some useful links. These are links to for more information on SOSA on our website. And then the technical standard snapshot 3 is available at this site. If you want to join SOSA, here's a link for joining. In VITA, you can also get involved with VITA, join VITA, and become part of a working group that's important to you. And all in all, I'd just like to say that we're going to see a lot more of SOSA in the future. And we are already seeing how important it is to the industry. So with that, I'm going to turn it back over to John and see if I can do that. Let's see.
Thank you, Rodger. Excellent presentation as always. And before I turn over to our next speaker, just a reminder to the audience to send your questions in, get them down, and we'll get them to our next speaker, whose name is Duke Tran of Aitech. Duke, the platform is yours, sir. Take it away.
Hello, everyone. Rodger just talked about SOSA and VITA, and what I'm going to talk about now is SOSA and Phase, how those two work together. This is something that we're currently doing here at the Aitech to incorporate both SOSA and Phase into our entire product line. Next slide, please. So open standards across the military platform, I think the benefits are fairly obvious. We're talking about strengthening the ecosystems, and we have the defense industry who's moving towards a lot more partnerships, a lot more integrated systems. The systems are getting more complex. So having open standard makes all that possible. It allows for technology insertions to be a lot faster than what it was in the past. Technology is obviously moving at a very rapid pace. The other thing is about compatibility between different products. Things just have to work together with different vendors, and also it allows for upgradability. And also it allows to do all these things in a much quicker and cost-effective way. And also the supply chain for the entire defense industry is also very complex, and it allows for more reliable supply chains for the industry. Okay, next slide. And the best way to understand SOSA and phase and VITA, SOSA is essentially the hardware side of, and phase is the software side of it. And the key here is the interoperability. This is an industry that we want to rely a lot more of the software element. We want to have develop applications without having to do that from scratch every single time. And this will certainly keep the cost down, help speed to the market, and allow for more integrated platforms. The other thing is the line between software and hardware also is becoming blurred, and you have hardware that is becoming much more digitized and has some intelligence built in, and SOSA recognize that and incorporate some of these software capabilities within it. So you can see that hardware and software are convergent. It's definitely happening. Okay, next slide, please. Some of the key phase technical standards. Phase is something that gets started in the avionics applications, and it finds its ways into mission-critical platforms. The use of in military, many systems as considered critical platforms. So you can see why its phase is highly adopted as a standard to be able to do that. Some of the great things about phase is that it's hardware agnostic. You can tie various hardware with various interfaces, but still work together. The benefit of it is there's better integrations and interoperability issues that can be reduced. Sustainability and scalability. A lot of the platforms that are operating in this space will last for 10, 20, 30 years or sometime more. And in that time frame, the program will be upgraded through the life cycle of it. And it allows for technology insertions so that you can insert new technology without having to redesign something every single time. And with all of that, it makes the system much more affordable, and time to market is faster, and adding more capability. Okay. In terms of the technical and business, just a quick snapshot at it. Phase is a government industry developed software standard I've already mentioned. And on the top picture here, it's essentially, instead of having closed interface in terms of software components, middleware, and OS, you have open interfaces. And the picture at the bottom gives a really clear indication of what we're talking about. If we use a simple example of a light bulb, you can have multiple light bulbs, but if all the interface is different, you're going to be spending time swapping the socket as well as the light bulb. And with having phase and SOSA together, you're able to simply having multiple different types of light bulbs, but the interface, everything is standard. And it allows for cross-platform modularity. It allows for off-the-shelf software marketplace, and it's really allowed for open architecture initiatives. Okay. So when we look at SOSA and FACE together, the benefit is lead us to something what we call a digital backbone. And let me just go to the next slide on that. So what is a digital backbone? So now that you've understand what FACE and SOSA is, this is an example, an illustration of how these two work together, and what kind of applications we can create. One of the concepts at Aitech that we've done is something called digital backbone. And if you think about the analogies of a human, the brain is the processing unit, the sensors are the inputs, the actuators are the outputs, and the spine is where the information flows between all the sensor, the actuators, and the brain. And by having a common infrastructure would not be possible without having a standard SOSA standard or FACE standard. And also by having a digital backbone, you can integrate, you can add more sensors, you can add more actuators, you can grow over time. You don't have to redesign something from scratch every single time. And this fits the requirements, and you can design this for multiple applications. And each application can have a different set of requirements. It could be based on SWaP-C, it could be based on performance is different, the scalability, ruggedization level also will be different. So this is one of the applications that we see when you combine SOSA and FACE together into these digital backbones, which is something that's pre-integrated, fully verified, and everything. Okay, next slide. Some of the different verticals in terms of digital backbone that if you combine SOSA and FACE, you can apply this digital backbone through, in fact, many different type of systems. Even though the product may look very different, the concept is very similar. The only thing that is different is the order of priorities. Which one is more important than another? Is it SWaP-C is more important? Is it scalability is more important? But the concept is the same across the board. So it could be drones, vertical lift, UJV, and small sats. And these are some of the current projects that we're working on. Just a very quick example of a UGV that we're currently working on. We would optimize it for example, in a SWaP-C, we would optimize it for cost, and as opposed to weight, whereas a vertical lift will be more weight. So this would be an example of what the digital backbone would be in real-world application. Okay, and so what are the benefits when you look at that? So between SOSA and FACE and building a digital backbone based on that, we estimate that the cost could be up to 50% compared to legacy architecture. And you can see that if you have a standards that can easily, different vendor can work with each other, you can see that the reduction is can be quite substantial. Also, it benefits the ease of integration of third-party components, and also this is a standard that, even though it's a U.S. standard, we see application in other part of the world. We have a customer from other part of the world. For example, some of our customer in Israel, they're asking for a SOSA and product because of these integrations of third-party components that is done in allied countries. And the other benefit is not just the development time of it, but the life cycle of the whole product. So you can add features much more easily. You don't have to build something from scratch every single time. And then the final benefit is really when you is kind of like increased confidence, because once you build digital backbone, you kind of pre-integrate, pre-test, pre-verify, pre-secure everything, and so you can add features in the future in a much easier way. And also the way the supply chain is today, where the supply chain is taking bigger and bigger component of it, this is something that is very useful. And so we at Aitech, we are part of the VITA, SOSA, and FACE, and we are incorporating into 4 areas of our product line. One is the single board computer, the other one is plug-in cards with GPU capabilities, data and control plane Ethernet switch, and power supplies. And on the side here, these are 2 of the recent products that we've got. With that, I'm going to pass it back to John.
Thanks, Duke. Excellent presentation. Another reminder to our audience to get your questions in, because after our next speaker is done, we're going to start our Q&A. And speaking of that next speaker, I'm going to turn it over to Dinesh. It's yours, sir. Take it away.
Thanks, John. Rodger and Duke have already discussed how SOSA leverages existing standards and specifications. So I'll kind of dig deeper and talk about how SOSA aligns with HOST and RedHawk. So we learned that that SOSA embraces many different and existing specifications and standards to meet the needs of the different services. This Venn diagram shows the specification overlap between HOST, RedHawk, and SOSA. The Mora specification has been added to link RedHawk to SOSA. The important thing here to note is that VITA is generally the primary overlap that ties many of these standards together. So let's dig deeper and focus on HOST first. So here's a table comparing HOST and SOSA at a very high level. The HOST 1.0 spec was released about 6 years ago by NavAir, while the SOSA 1.0 spec, as Rodger had mentioned, is started to release this year. The SOSA 1.0 specification is almost 10 times more verbose than HOST, and as we just learned, it's a broader and more inclusive specification. We can see that both HOST and SOSA share VITA and OpenVPX standards, but how well are they aligned? In looking at the different OpenVPX slot profiles, we see that there is alignment between HOST and SOSA, but there are some slot profiles in HOST that aren't a part of SOSA, and those are highlighted in yellow or orange on the slide. Even in the shared slot profile, where you see SOSA has like 1 equal legacy, so that's kind of a shared slot, but we can see that some of the modules are being deprecated, module profiles are being deprecated in SOSA, but are still active in the latest HOST 4.0 spec. So it's clear that SOSA incorporates much of the HOST spec, but not everything. We can't assume that there's 100% alignment between one spec and another. So what this means is if a program requires conformance to have, if a program requires conformance to 2 relatively close specifications, like in this case between HOST and SOSA, double checking both specifications for commonality is really important. One thing I forgot to mention in the slide is that there is another difference between SOSA and HOST. SOSA explicitly calls out support for VITA 49.2, while HOST does not. We will see why this is relevant next. So let's move on to RedHawk. So what is RedHawk? RedHawk is a popular open source framework used to build software-defined radio applications. The code is available for download from GitHub. RedHawk leverages the software communication architecture, a component-based development programming model released by the Joint Tactical Networking Center. The block diagram gives a simplified high-level view of the RedHawk framework and how it sits on top of the operating system and hardware. The key benefit of SCA is it separates the software from the hardware. This allows the RedHawk application to be written in software that's independent of the target hardware it will be used on. This makes RedHawk code reusable, portable, and scalable across different radio hardware. So RedHawk is composed of 3 primary containers of abstraction. The first is the domain, or the project file, which contain multiple instances of waveform containers and node containers. The waveform containers have components. The components are the primary processing blocks of a radio, such as a filter or a demodulator. Multiple components are connected together like building blocks to create a more complex signal processing chain called a waveform. An example of a waveform included in the RedHawk libraries is called RBDS, which extracts digital information from an FM radio by using tuning, filtering, demodulation, and decoding components. The node is a proxy for hardware and can be seen as a device manager for processors such as an x86, an ARM, or an FPGA. The node is where the waveforms will run. Connections are made between the ports of waveforms and nodes with the corresponding resources managed by the domain. This maintains separation of software and hardware. SOSA incorporates portions of the Mora specification, which itself is an extension of the U.S. Army's Victory standard. Mora has the same goals as SOSA in terms of interoperability between modules, but for the RF domain. The SOSA specification defines a communication link between a SOSA module and a Mora module. This is done through the Mora low latency bus for data and context and the Victory data bus for system management, all of which follow the Mora spec. Both SOSA and Mora allow for intermodule communication through VITA 49.2. For this example, we are assuming that both the Mora RF module and the SOSA module are following the VITA 49.2 standard. RedHawk has an option to support VITA 49.2 through libraries that can be compiled into the waveform. By building these waveforms to be VITA 49.2 compliant, the RedHawk application can then be targeted to a processor on both a Mora compliant or SOSA compliant board. For example, we could run a portion of a RedHawk waveform on an FPGA on a Mora module for the RF domain, while also running another RedHawk waveform on a SOSA x86 module for digital processing. The link between Mora and SOSA would be through VITA 49.2, which is supported by both specifications. This is a modular solution that provides the best of both worlds. The RedHawk waveforms remain portable, reusable, and flexible, while the hardware maintains interoperability, scalability, and upgradability through Mora and SOSA. So coming back to HOST, because HOST does not explicitly support VITA 49.2 or the Mora spec, such a modular solution may not be possible with HOST. So to summarize what I covered today, number one, SOSA is doing a great job of leveraging existing standards and specifications. It is not trying to reinvent the wheel. However, as we have seen in the case of HOST, even though there is significant overlap, it is not 100%. What this means is, if a program requires support for SOSA and an overlapping standard such as HOST, then double-check both specifications to make sure that the solution falls within the intersection of the Venn diagram of both standards. In addition, SOSA's broader inclusion of multiple different standards, such as Mora and VITA 49.2, gives greater flexibility in building modular and interoperable systems. Number two, it is possible to align RedHawk with SOSA. One way to do this is to leverage the Mora hooks within the SOSA specification to connect the RF and processing modules through VITA 49.2. RedHawk has VITA 49.2 library support, and the solution needs to be architected such that modularity and interoperability can be maintained, and this is possible through SOSA. Much work is being done in this area, and solutions are coming, so I'm expecting more discussion on this topic in the future. And finally, number three. So repeating what my colleagues Rodger and Duke have said, architecting a solution that follows the SOSA standard will give portability, scalability, upgradability, interoperability between different SOSA-compliant modules. It is for this reason that I'm excited about the upcoming release of the SOSA 1.0 spec. I truly believe it will drive innovation and enable rapid deployment of the latest technologies through collaboration. And with that, I would like to thank you all for your time today. I've included some links for resources for a deeper dive of what I've just covered. And with that, back to you, John.
Thanks. Excellent presentation. Dinesh, excellent presentation, all three speakers. Let's get to that audience Q&A. First question from the audience. This one is for AI Tech. When we talk about standardization, how do we see existing standards and like SOSA and the face standard playing a part? I'll give that one to Duke.
Hi, thanks for the questions. I think I talked about in my presentation is that some of the things that we're building as the digital backbone would not be possible without it. And SOSA is the hardware component of it, and face is the software. And having the SOSA and face together, this is when all these things is possible. And it allows for all the stuff that I think all three of us have mentioned today, which is interoperability, lowering cost, increase speed of development, future-proof some of these items. And we have a couple of products that we've introduced this year, such as the UC877 and UC5300, and these are some of the example of a SOSA-based product that we bring into the market.
Thanks, Duke. Next question from the audience. Do the compliance requirements sufficiently specify requirements so that items intended to be interoperable need not all plug together before compliance is confirmed? I'm going to throw this one at Rodger.
Okay. I think, let me just think about this a minute. Before compliance, the whole idea is that we have to, in defining the conformance process, you have to define everything that this particular product must comply and conform with. And once that list is done, that's all that the vendor has to meet. Now, if the list is incomplete because somebody forgot a certain critical part that needed to be added to the list, then that's really the fault of the list of compliance items. So it's really a tough job to, first of all, define everything and think of everything that will need to be conformant and compliant. But once that list is done, and your board meets everything, you will be certified to be conformant. Now, I guess so the question is it perfect? No, but it's going to be pretty good to start with. And then, but there isn't a requirement that you have to operate with different boards. You just have to meet the specifications that are specified, in that list to meet that conformance specification. I don't know if I answered the question or not, but in other words, you don't have to test it with every other board in the market or with certain boards even. You just have to prove that it meets the requirements as defined in the conformance specification.
Thanks, Rodger. Anybody else want to take a stab at that? Okay. Next question from the audience. Examples of existing OpenVPX modules have been referenced to be adopted into SOSA. What OpenVPX backplane profiles will be adopted? Rodger or?
Well, yeah. If you take a look at the snapshot 3, what you'll see is a very good list of which ones are. There are both 3U and 6U profiles, and by the way, this is not yet final, of course. But if you take a look in there, you'll see that there are a couple of handfuls of different VITA 65 specifications that have been adopted. So that's really the source of the latest information, the latest answer to your question.
Yeah, and if I could add to that, if you can get your hands on the snapshot that Rodger's referring to, the slot profiles are pretty well defined. I think I'm going to go out on a limb and say that they're close to final. So Of course, nothing's final until we get the release of the spec, but the specification does go into detail about what the slot profiles are being adopted.
Thank you, gentlemen. Next question from the audience. Is there a roadmap of capabilities which will flow into silicon? This person is thinking of how to shrink the footprint of nodes on the SOSA fabric. With a follow-up, or SOSA designed to only work with boards on a backplane? Dinesh, I'm going to let you answer this one. And then Duke and Rodger chime in if they like.
Sure. I think as far as the actual physical interfaces are concerned, that's going to rely probably on the OpenVPX backplane. But the actual connections into what we're looking at is how can we reduce the amount of silicon that can be taken up on the board. And what we believe is that by specifying the standards, whether it's gig E, 100 gig E, 400 gig E, copper, optical, traditionally those tend to be different modular components on a PCB. And the beauty about specifications and standards is that if you're a silicon vendor and you know that, okay, this thing has been defined and we know for sure that this will be used in a solution, and I can take the risk to integrate that into my silicon and absorb the cost because I know that the market is there for it, versus it may or may not be involved or whatever. So I think what will happen is there'll probably be a bit more silicon absorption of the different IP blocks. And I think where that will start initially will be the FPGA. So Rodger had shown some block diagrams of the RFSoC. And I think as a first step in terms of silicon integration, it'll start at the FPGA level, since that's relatively easier to do. And then eventually, over time, that should find itself in ASICs and potentially even CPUs and GPUs and so forth over time. But I think it'll start with FPGAs and probably SoC silicon type chips, and eventually lead to greater and greater integration, which will reduce the chip count on the PCB.
Yeah, exactly.
Anybody,
right.
Duke or Rodger? Go ahead.
Yeah, I was going to bring up the RFSoC as an example, which was a good one. But think about what again this gray box concept is, where you basically need to define your interfaces and how do you connect to other modules, but there's no limitation on what you're doing inside. And so you can have, different generations of silicon that have more advanced and higher density, more channels, more processing power, put into this gray box concept on a board, on a module, and, for example, double the processing power or double the number of channels of sensor processing, while still fully meeting the requirements of SOSA for the interfaces. And so I think that's the way it's going to grow. Remember too that you can also have connections to a remote sensor that might be up on an antenna that could be connected up through, let's say, a VITA 49 optical data link that goes into a SOSA system. So you while the sensor up on the antenna and its subsystem up there isn't a VPX box, it's connected to a SOSA system that really is what SOSA controls. It doesn't control every arm and every leg in the sensor at the sensor level, but it controls the interfaces to those elements that are connected, and it's quite well thought out.
Thank you, Rodger. I had a quick follow-up to the question that was asked before about VITA 60, OpenVPX, VITA 65. Where in snapshot 3, because I cannot find the backplane profiles. Could you elaborate on that?
Yeah, the backplane profile? Is that you
Yeah.
couldn't find that in VITA 65?
That's what the person said. Yeah.
Okay. Well, there are backplane profiles that have been adopted. One of them, and I can't quote the number, so and I don't know that the chapter or the section where that is defined. But I know that Elma, for one, who's a backplane manufacturer, is offering a SOSA-aligned backplane in multiple different flavors. So,
Okay.
So I mean that's how we're putting together SOSA-aligned systems. We're using those backplanes which are aligned.
Okay. Thanks, Rodger. I've got a question here for Aitech. Aitech has a lot of history of running open standards-based boards in space, like compact PCI. I know there's also space DPX coming out, and looking how SOSA works so closely in those standards. How will SOSA standards be applicable to space applications, Duke? If so, how?
Yeah, it will be in some instances. It's not going to be widely adopted the way, because in the million aero, it's driven by government and industry is on board. But it doesn't stop Aitech from bringing SOSA product line into the space. So, and one of the things that's happening in the space is that a lot of the newer space applications is in the low orbit. So you have Elon Musk sending thousands of satellites that operate in low orbit, and you have a lot of other constellations that is sending satellite in a low orbit. And a low orbit application is a lot closer to what a million aero application is. Whereas if you send it into a geospace, geostationary, where these $500 million satellite is not so applicable. And so where the market is going, we see very much certainly an appetite to bring more COTS-based systems, and some of these COTS-based systems happen to be SOSA and phase aligned. This is not necessarily driven by the government, but it could be something that is driven by us as to bring some of these products into space that is much more affordable when you compare to a pure space grade product. So definitely it's something that it's starting.
Thanks. And while it might not be designed for space requirements, it might in itself be applicable to space requirements, which is why you would design a SOSA board into a system. Yeah. Thank you. Next question from the audience. This person is trying to better understand the compliance hierarchy. Can one, for example, achieve MOSA by conforming to FACE but not be SOSA compliant? Who would like to tackle that?
I can maybe take a stab at it. This is Dinesh. So I was as I was researching the kind of the RedHawk application and how that would work. One of the things that I kind of ran into was certification and compliance and stuff. So I think the key thing to understand here is that every standard may or may not have their own compliance and certification requirements. We do know that SOSA will have one as soon as the spec is launched. There's going to be a compliance testing, and it's going to be tested against the SOSA spec itself, right? So whatever's in the SOSA spec, that's what the vendors who are building the modules will have to pass in order to claim that they're SOSA compliant, and even put a badge on their product saying that they're SOSA compliant. Now, if as the overlay or the overlap in the Venn diagram shows that if there's 100% overlap, like for example host and SOSA, one can argue that if it passes SOSA, then it should pass host if everything aligns. I'm not aware of any such interaction between the two standards, but we could probably push that case if we wanted to. But SOSA is going to stand on its own, and any other standards like MOSA, for example, If they happen to fall into that, we could make the individual case to say that it is MOSA compliant as well, but that is not the purpose of the SOSA compliance program. So it's kind of, it's really targeted at SOSA.
Anybody else
I hope that
want to
answers the question.
No, thanks, Dinesh. Okay.
Yep.
Next question from the audience. How robust do you see this equipment in regards to conducting asynchronous updates of transport media and processor level upgrades? Anybody want to take a stab at that?
Let's see. I'm not sure I understand everything, but there's definitely. Are you talking about? I don't know if we're talking about hardware upgrades or software upgrades or firmware upgrades. There's a lot of ways of inserting some new technology, and one is with hardware, and one is reconfiguring the existing hardware through programmable, FPGAs, software, and so forth. So those async upgrades are extremely important to military operations. For example, the ability to detect a new waveform, a new threat, a new countermeasure, a new targeting system, or something. That's clearly an upgrade that may need to be done very frequently, and hopefully, in most cases, that could be done simply by loading a new software firmware package into the existing hardware. So I'm not sure if that answers the question or not, but the whole mission of SOSA, the main objective, is to allow for reconfigurability and easy upgrades, new technology insertion, and so anything that locks in a particular mode of operation that should really be something that's configurable would be antithetical to what SOSA is trying to achieve.
Thanks, Rodger.
Yeah, I want to.
One more. Go ahead, Dinesh.
Yeah, go ahead.
Yeah, please do.
I just wanted to add to that, because there's many different ways of interpreting the question, but it really depends on what's being. It's about modularity and interoperability. So there's multiple ways, whether it's a software update or hardware update. The key is that whenever the updates happen, that the pieces that remain have to still work together, and that's the focus of SOSA, while still maintaining security. And that's the other piece that I wanted to bring up, which is that we have this modular thing, but SOSA also incorporates many security features to ensure that the products are tamper resistant or tamper proof or tamper resistant.
Thanks, Dinesh. Last question, and it's interesting because the standard isn't done yet, but it says technology is continuously moving forward. How long do you expect the SOSA standard to stay relevant? So I guess a better question would be is why is it relevant now? And I'm going to give that one to Rodger.
Okay. Yeah. I mean, any standard that doesn't evolve is probably not a very good standard, because that means nobody's using it and nobody's pushing anything, forward with new technology and new requirements. So by definition, in my mind, a good standard is one which is constantly evolving. Hopefully not every day, but certainly on a regular basis, to embrace new ideas, new technologies, and to achieve new capabilities. So, and to the other part of it is, what we're seeing already is we're seeing a lot of government contracts are requests for bids and so forth are talking about open systems architecture, compatibility, compliance, and designed with the open systems architecture in mind. And as soon as the standard is released, I believe that wording will be more strongly a requirement to comply with a certain release of SOSA. And so if it's coming from the government, US DOD, everybody is going to be paying attention to it and trying to comply with it and try to have products that will meet a particular government bids requirement. and that will keep it going. I don't see the government turning away from this. In fact, I see them becoming even more committed to SOSA each year. There's a tremendous amount of support, and they're putting their money where their mouth is in terms of moving that in that direction on procurement activities as well.
Thanks, Rodger. And that brings us right up to our time limit for today. Sorry we cannot get to all of your questions. I'm going to get back to you after the webcast with more information. I want to thank Rodger, Duke, and Dinesh for speaking today, and Aitech, Pentek, and Smart Embedded Computing for sponsoring the event. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will be archived online today and be available for 1 year. There'll also be an MP3 version of the event available. Thank you all for attending. I look forward to seeing you in future Open Systems Media webcasts. Goodbye.